Section 3.7, Inverse Functions. In this section, we're going to verify inverse functions, determine the domain and range of an inverse function, and restrict the domain of a function to make it a one-to-one function. Find or evaluate the inverse of a function. Use the graph of a one-to-one function to graph its inverse on the same axis. Here is a warm-up activity. We're going to find f of g of x and g of f of x. So the first one is f of x is x minus 3 and g of x is x plus 3. So f of g of x, f of g of x is basically f of g of x, which means we're going to plug g of x instead of x for f of x. So it's going to be g of x minus 3, which will be x plus 3 minus 3, and that will give us an x. The other one, which is g of f of x, which is g of f of x, that means we're going to say it is f of x plus 3, so we're going to plug g of x instead of f of x in g of x. So that is going to be x minus 3 plus 3, which will give us x basically. The 3's are going to cancel together. And the second one is the same. So if we find f after g or f of g of x, that is basically f of g of x, which means we're going to say g of x cubed minus 3, and that will give us the cube root of x plus 3 all cubed minus 3. Notice how these are going to cancel together. So we will end up with x plus 3 minus 3, which will give us just x. Similar with g of f of x, that is g of f of x, which basically is the cube root of f of x plus 3. That is basically the cube root of x cubed minus 3 plus 3. These will cancel. That is the cube root of x cubed, which is equal to x. So all of these answers are equal to x. This will lead us to the next big idea. The formula for converting Fahrenheit to Celsius is given by C is equal to 5/9, F minus 32, such that C is the temperature in Celsius and F is the temperature in Fahrenheit. This basically takes the input F, which is the degrees in Fahrenheit, and the outputs are C, which is basically the temperature in Celsius. If we rearrange this formula to convert Celsius to Fahrenheit, we get F is equal to 9/5C plus 32. This takes an input of C and output of F. This second formula right here, the second formula is basically the one that corresponds to the idea of an inverse function, which is basically a function for which the input of the original function becomes the output of the inverse function, and the output of the original function becomes the input of the inverse function. In other words, it undoes what the original function does. Given a function f of x, we represent its inverse as f inverse of x. So we represent it in this notation, and this is an inverse. It is not a power of -1. So f inverse of x is read f inverse of x. The -1 here is part of the notation, and it's not an exponent. So you should not think that it is a power of -1, okay? So we know that the power of -1, let's say 5 to the -1 is basically 1/5. This isn't the same. This is just the notation for the inverse. It does not imply a negative power, and I can't emphasize that enough. When we perform a function composition of the inverse function and the function, we will get x always. So to check if two functions are inverse of one another, we have to prove that f inverse of f of x is equal to x and f of f inverse of x is equal to x. So we have to do it both ways and prove that both ways the result is equal to x. So I can safely say that the function f of x and g of x in example A are inverse of one another because f of g of x and g of f of x are both equal to x. Same with example number B. Here is another example. If you have f of x is equal to 4x and g of x is a quarter x, these are inverse functions. Show that f of g of x is equal to x and g of f of x is equal to x. So again, f of g of x is basically f of g of x. We're going to remove each x in f of x and replace it with g of x. So that is 4 times g of x, which is basically 4 times 1/4 of an x. Notice how the 4 is going to cancel with the 4, and the final answer here will be x. This is not enough. We have to prove the other way, which is g of f of x is equal to x as well. So let's prove it. So this is g of f of x, which basically we're going to prove each x in g of x with f of x. So it's going to become 1/4 times f of x, which will be basically 1/4 times 4x again. So these will cancel together and we will end up with the answer x. So we proved that f of g of x equals g of f of x equals x. If u coordinates pairs from the graph of the function f of x equals 4x are -2 and -8, 0 and 4, 2 and 8. And if u coordinates pairs from the graph of the function g of x equals 1/4 x are -8 and -2, 0 and 0, and 2 and 8. Notice how if we interchange the input and the output of each coordinate pair of a function, the interchanged coordinate pairs would appear on the graph of the inverse function. Note that not all functions have inverse. Not all functions have inverse. I'm going to give you a very simple function here. So let's say that r equals 2, 3, -1, 3, and -2 and 4. Okay. This is a function. We know that this is a function because each element from the domain is paired with only one element from the range. So this is basically a function. However, if you're going to find the inverse of that function, basically you're going to flip the pairs or basically interchange x and y. Notice how the inverse is not a function. Okay, so the function r that I defined with the 3 ordered pairs does not have an inverse because the inverse is not a function. Why is it not a function? The problem lies here. The 3 is mapped to 2 and it's mapped to -1 as well. That is a problem because we know that in a function that cannot happen. One element from the domain cannot be mapped to 2 elements from the range. Remember the example of the taxi taking 1 person to 2 places at the same time. This is impossible, which means this function specifically, r, does not have an inverse. Why is that? There is a specific function, there is a specific type of functions that have an inverse. These functions are called one-on-one functions, and we spoke a little bit about one-on-one functions in the past, and we said each element from the domain is mapped exactly to one element from the range, and the mapping could look something like this: 1, 2, 3, A, B, C. So 1 is to A, 2 to B, and C, 3 to C. So this is a one-to-one function. Versus if you draw or graph the function r, you will notice that the element 2 and -1 go both to element 3 from the range, which makes it a not one-to-one function. So this is not one-to-one function. It is a function, however, it's not one-to-one. So any function that is not one-to-one is not going to have an inverse because the inverse is not going to be a function. That is what we have for now. Later on, we're going to learn something else that can help us find the inverse for functions that are not one-to-one functions. So if we want to determine whether a function is one-to-one, we have to define a one-to-one function first. So a one-to-one function is a function in which each output value corresponds to exactly one input value. There are no repeated x's or y values. This means the function must pass both the vertical line test and the horizontal line test. So the function must pass both tests. And for every x, there can be one and only one y associated with it. So the previous example are this example right here. This function does not satisfy these conditions, which means it's not one-to-one function. Domain and range of the function and its inverse. The outputs of the functions f, the outputs of the function f are the inputs of the inverse function f. So the range of f is also the domain of f inverse. Likewise, because the input of f are the outputs of f inverse, the domain of f is the range of f inverse, and we can visualize it with the situation below. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse, because when we find the inverse of the function, we're basically interchanging x and y. So x becomes y and y becomes x. When a function has no inverse function, it is still possible to create a new function where that new function on a limited domain does have an inverse function, which is called limiting the domain. When we limit the domain, we take some values such that the part that we take is going to be a one-to-one, and then we can find the inverse for that part. For example, the inverse of the square root of x is x squared. The f inverse of x, the square root of x, is basically x squared, but the square is only the inverse of the square root on the domain from 0 to positive infinity, since that is the range of the original function, which is f of x equals the square root of x. Notice here is the square root of x function. Notice how the domain is restricted from 0 to positive infinity. That is the domain of the original function. So the inverse of that function is this part of the quadratic. Why is that? Because that is the only part that happens to be in the same domain as the square root function, which is basically from 0 to positive infinity. The other part is not actually the inverse of the square root function. Restricting the domain to 0 to positive infinity makes the quadratic function, makes it a one-to-one function. So it will pass the horizontal and vertical line tests. So it has an inverse, but that inverse has to be restricted on the restricted domain. Here is an example. The following graphs will not pass the horizontal line test. Restrict the domain of the following functions such that all range values are included. So in the first case, I can take half of the function. Notice how the domain I restricted this function to is from 0 to positive infinity. So I'm going to restrict it from 0 to positive infinity. For the second function, I will just have half of it. So I will just take half of it, which, if you look at it, it is restricted from 2 to positive infinity. So I'm going to restrict the domain here from 2 to positive infinity.